Here's an example where we're finding the coordinate vector for a polynomial. So we're working within the vector space P2, the polynomial's degree 2 or lower. So we're letting B equal this collection of polynomials here. So 1 minus t squared, t minus t squared, and 2 minus 2t plus t squared, which is an ordered basis for P2. So again, just quick review, basis. The requirements for a set like this to be a basis are two things. One, that these polynomials are linearly independent, and two, that these polynomials span all of P2. So meaning we can take any polynomial in P2 and write it as a linear combination of these three quote-unquote vectors, in this case polynomials. Ordered basis just means that the order of the polynomials within this set has significance. So yeah, just this is our polynomial number 1, this is our polynomial number 2, this is our polynomial number 3. When we find a coordinate vector, which is what this notation here means, for a certain polynomial, that means that we're looking for the weights. So draw a line here. So we're looking for the weights C1, C2, C3, where C1 times first polynomial here, so 1 minus t squared, plus C2 times the second polynomial, t minus t squared, plus C3 times the third polynomial, so 2 minus 2t plus t squared, is equal to our given polynomial. So 3 plus t minus 6t squared. Is that showing up? Yeah, okay. Okay, so we need to solve for C1, C2, C3. And then this vector, our answer here in the end, is going to be a three-dimensional vector with these three scalar entries, whatever C1, C2, C3 are. So let's multiply this out. The plan is to multiply everything out here and then collect your powers of t so that we can match up the coefficients of the given polynomial here with the coefficients on this side of the equation. So C1 times 1 minus C1 times t squared, C2 times t minus C2 times t squared, C3 times 2 minus 2 times C3 times t to the first plus C3 times t squared. Okay, equals this. All right, let me introduce some color to this. So collecting terms, and I guess I'm going to use the same order that I have over here. So I have the constant first. So constant terms are here. Those all involve t here. And that's it. So the constant term on this side is going to be C1 plus 2C3. Okay. Now I have 1 t to the first on this side. Let's combine the t to the first terms on this side. So C2 times t, negative 2C3. So we have plus t times coefficients of t are, this was positive 2C2, or sorry, positive C2. Minus 2C3. Okay, and then I don't have my green handy. Oh, sorry guys. Like I told you, they're low-tech recordings, so you have to put up with me opening my Expo. Okay, here we go. T squared terms. So negative C1 times t squared, negative C2 times t squared, and positive C3. So plus t squared times negative C1, negative C2, and positive C3. Okay, sorry, that green's not showing up too great. But so we match this up with the coefficients on the right-hand side of this equation. So the the constant term is 3. The t to the first term is positive 1 times t. And then the t squared term is minus, oops, this is not green. minus 6t squared. So match the constant term on this side with the constant term on this side. So that gives us c1 plus 2c3 must equal 3. Match the coefficient here, which is c2 minus 2c3, with the coefficient of t to the first here, which is 1. So c2 minus 2c3 equals 1. And then last one, match the coefficient here with the negative 6t squared on this side. So negative c1 minus c2 plus c3 is equal to negative 6. Okay, so we've got 3 equations with 3 unknowns. We can actually solve this system with substitution. So if I can avoid setting up a 3 by 3 or 3 by 4 matrix and row reducing it, then I prefer to do that. So in this case, this first equation, c1 plus 2c3 equals 3. And we could do this. I'm going to copy it here. c1 plus 2c3 equals 3. So c1 equals 3 minus 2c3. And c2 minus 2c3 equals 1. So c2 equals 1 plus 2c3. And now if we substitute both of those expressions into this last equation that I have in green, then we can solve. So negative c1 minus c2 plus c3 equals negative 6. But c1 is 3 minus 2c3. And minus c2, sorry, I need a better black. I'll have to just stick with this one for now. Oh, no, actually. Okay, so minus c2, which is 1 plus 2c3, and then plus c3 right here. So plus c3 equals negative 6. Okay, so when we combine, let's see, when we simplify this, so this will be negative 3 plus 2c3 minus 1 minus 2c3 plus c3 equals negative 6. Combine like terms. So 2c3 minus 2c3. Oh, that's convenient. So those cancel each other out. And so we have just c3. And then negative 3 minus 1, as long as I've kept track of my signs properly, then this is negative 4 when you put that together, equals negative 6. And so c3, if we add 4 to both sides, c3 equals negative 2. Bring that over here. So if c3 is negative 2, then this is 3 minus 2 times negative 2. So that'll be 3 plus 4. That tells us that c1 is 7. And then c2 is 1 plus 2 times c3, which we know now is negative 2. So that'll be 1 minus 4, so negative 3. And so with all of that, this tells us, I'm going to write it on the bottom here, that the coordinate vector for the polynomial 3 plus t minus 6t squared for this particular ordered basis is c1 is 7, c2 is negative 3, c3 is negative 2. So this right here is our coordinate vector. This is exactly the same as the way you would do this if you had an ordered basis involving, your traditional column vectors. You would set it up the same way. We'd set up c1 times the first vector plus c2 times the second vector. plus C3 times the third vector equals the given vector. Sorry, my phone's ringing. But so here's our final answer.